Okay, let's dig in on concurrency control. Remember, the concurrency control exists to provide isolation across multiple transactions. And the naive approach to achieve it is to simply forbid concurrency and only allow serial execution, where one transaction is running at any given time. This is safe, but it's slow. As we discussed, we would like to have interleaved actions from multiple transactions to get better performance, and in essence to allow background tasks to work on our hardware while we're computing foreground tasks for our transaction. With concurrent execution, though, problems arise. The first is, how do we define what's correct behavior? What interleavings of actions should be allowed? And then the second is, how do we ensure that correct behavior? So in the coming slides, we'll look at both of these issues, beginning with definitions and formalisms for correctness, and following up with mechanisms to achieve that formalism. We'll start by defining what we call a transaction schedule. A schedule is a sequence of actions on data from one or more transactions. These actions can include beginning a transaction, doing reads and writes on particular objects in the database, and then concluding with a commit or abort for the transaction. Of course, we have to start with a begin, and we end with one of commit or abort. We'll use two sorts of notations to notate transaction schedules. On the left, we see a tabular schedule notation, where every row is sort of a time slot and every column is a different transaction. And so you can expect only one value to be filled in per row from one of the transactions, but they can be different columns on different rows. Okay? And in the middle of the slide on the right, we see a string representation of a schedule, which corresponds in this case to the table on the left. So we have a read by transaction 1 of A, a write by transaction 1 of A, a read by 1 of B, a write by 1 of B, and then a read by 2 of A, a write by 2 of A, a read by 2 of B, and a write by 2 of B. By convention, in the string notation, we'll only include committed transactions, and we will omit begin and commit unless they're necessary for discussing what is going on. Given a definition of a schedule, we still need a touchstone concept for correct behavior. And the one that we can work with, because we're familiar with it as programmers, is the notion of a serial schedule. So a serial schedule will look something like this picture on the right, in which each transaction runs from start to finish without any intervening actions from other transactions. This is the behavior that we've long known how to program in a computer. It's like having the computer to yourself, complete isolation. Having gotten a definition of a serial schedule, let's talk about a definition of two schedules being equivalent. So we'll say the two schedules are equivalent if they satisfy the following three properties. They involve the same transactions. So these two different schedules have the same columns with the same actions in each column. And each individual transaction's actions are ordered the same. So as you go down a column, you see the same sequence of actions in the two different schedules. And then both schedules leave the database in the same final state. So one way or another, running these transactions in these two different interleavings leaves the database in the same state. If that's true, we'll say that the two schedules are equivalent. Having seen all that, we're now ready to define the property we're looking for, which is called serializability. We'll say that some schedule S is serializable if it is equivalent to some serial schedule. So if S is interleaved on the left and it's two transactions, there's two possible serial schedules, the first transaction before the second, or the second transaction before the first. And if we can show that S is equivalent to one or the other of these, we'll say that S is serializable. And when you think about serializability, it's pretty attractive. It says, I don't know what order these transactions happened in, but it's as if they happened in some serial order. And so they make sense in some version of the world. Another way I like to think about this is if you think about transactions as people queuing up, say to use an ATM machine at the bank. You don't so much care what order the queue is serviced in. You just want to make sure that somebody doesn't interrupt someone else while they're using the ATM. Each person who uses the ATM uses it in isolation. So if you can guarantee that concurrent uses of multiple ATMs give the same effect as some ordering of a queue at a single ATM, well then you know that things basically make sense. So note that serializability doesn't say what order the transactions happen in, just that a transaction schedule is serializable if it's equivalent to some serial schedule. So let's look at schedule 1 here. We've got two transactions. T1 is transferring $100 from A to B, and T2 is adding 10% interest to both A and B, multiplying each of them by 1.1. So here's a serial schedule in which T1 is followed by T2. And so in the final outcome, we first debit A and then give it a 10% interest. So A equals 1.1 times A minus 100. And in B, we first credit B with 100 and then multiply it by 1.1. to give us 1.1 times b plus 100. Here's schedule 2, in which t2 is followed by t1. In the final outcome here, first we get interest on a, and then we subtract 100, making a equal 1.1 times a minus 100. And for b, we give it interest, and then we add 100, so it's 1.1 times b plus 100. Note that these two schedules have different outcomes, but each of them is a serial schedule, which means each of them sort of makes sense. We don't so much care whether t1 happened before t2 or t2 happened before t1. They're both valid serial schedules. Here's a third schedule that's interleaving t1 and t2's actions. It is not itself a serial schedule, but if you look at it, it is equivalent to the first schedule we looked at, schedule 1. In this case, a has 100 subtracted before it is multiplied by 1.1, and b has 100 added before it's multiplied by 1.1. So you get the same outcome as we got in schedule 1. Hence, schedule 3 here, it is not serial, but it is serializable because it achieves the same outcome database at the end with the same actions of the same transactions.